Alright, welcome back. So here's now our graphing of our polar functions. So, like with rectangular coordinates, we can simply plot these by plotting different coordinate points, all those special values there on the edge of our polar grid, and create our graphs. There are technically a little more efficient ways of going through this, and we'll kind of discuss that as we plot those different points. But at least in the beginning, it's better to use the calculator, find all the special values, plot them, and we'll discuss the different ways you can use symmetry and repetition from the unit circle to make the graphs. Um, so there's four main types of polar graphs we're going to take a look at. Circles, which we've discussed in its regular rectangular form, but there's a polar form for each of the circles. What's called limicons, roses, and lemniscates. So the circles, there's four different ways you can look at this circle graph. We'll look at one of them when we create it. It's based on r equals a cosine or r equals a sine theta. A can be positive or negative, and obviously it can be sine or cosine for each one of those. If A is positive and talking about cosine, it's on the right side, whereas if A is negative and its cosine is on the left side, and then top for sine when A is positive, bottom when sine when A is negative. So what we're going to do is we're going to fill out the table and then use that table to make this sketch. So what you're going to do is you're going to take your graphing calculator, you're going to go to mode, and you're going to change it from regular function mode to polar mode. And you're going to also want to make sure you are in radians mode for the different angles. Then what you're going to want to do from there is you're going to want to go to the y equals. You'll notice now it says R1, R2, and R3, and so on. And you're going to type in 2 sine theta, where theta is your variable in the same place you would type in the x. And then to find all these values and make your life easier, you're going to then hit second window that your table set. You're going to have it start at 0 and have your delta table be pi over 12 because you're seeing each space is pi over 12. And then you'll hit second graph to look at the table values, and they'll be decimals, but they'll be equivalent to each of these radian values in pi. And there will be a video on the TI-84 using the graphic calculator that will show you how that works out as well. But the idea is when you're using that, you're going to find these different points. So you're going to get a 0, 0 0.5, 1, 1.4, 1.7, 1.9, and then 2. And I'm going to stop there for the first quadrant so I can just kind of show you how the shape starts being created. For the decimal values, well, we want thousands place for most answers with decimals. I'm going to only want tenths place for these graphs just because you're not going to be able to plot the difference between 0.5 and 0.537 kind of thing. So we're not going to go too crazy. So 0, 0 is going to be right here in the beginning. And then our first line is pi over 12. It's going to be raised to 0.5, so it's in between 0 and 1. And then pi over 6 is at 1. Pi over 4 is at 1.4, so it's a little bit past the halfway spot. Pi over 3 is 1.7, so it's a little bit closer to the ring. 5 pi over 12 is at 1.9, a little bit closer now. And then pi over 2 is at 2. So you can see we've got this shape right here. We got half a circle created. So we continue on. So 7 pi over 12 is going to give us 1.9. And then we're going to get 1.7, 1.4. And this is what I was talking about before, the whole you recognize patterns here. Because now we're working on the other side. So we're going from the peak point at 2, working way back down to 0. So just repeating those same values in that same exact order. So then the next point's at that 1.9, the 1.7, the 1.4, 1, 0.5, and then back to 0. So here's the other half of it. And we've created a full circle. And you'll find for the other values here, you're going to get these answers will be the same 0.5s, 1s, 1 point, and so on, but they'll be negative. So this will say a negative 0.5, negative 1, negative 1.4, negative 1.7, negative 1.9, negative 2, and then negative 1.9, negative 1.7, negative 1.4, negative 1, negative 0.5, and then back to 0. But we don't need them because we've already completed our circle, so you'll find that these are plotting right over top the same other points. Because since r is negative, we're going to the 3, if I would go to 3 pi over 2, negative 2, positive 2 would be right there, but across the other side is back to the same spot which we already plotted. So when it comes to the circles, we actually need the coordinate points from 0 to pi to create our circle. Everything else after that is just going to be plotted right on top of it. All right, and again, we could do this without using the calculator in the table. It just requires us to, remember unit circle values, because this first one right here would be 2 sine of pi over 6, pi over sine pi over 6 is a half. 2 times a half is 1. That's where the 1 came from. And we can do the same thing for all the other ones, pi over 4 and pi over 3, pi over 2. The over 12s you really need to use the calculator for because that's just there to help create the full shape. But it's obviously not something we remember from the unit circle, at least if theta is just theta. If it was 2 theta, then 2 times pi over 12 gets us to pi over 6, and it is on the unit circle. And there will be some graphs that use that, but not for your circle shape. That's all we want for the circle. The limicons, there's 4 different types of them based on what's going on with the relationship of A and B, where the format is either A plus or minus B cosine theta or A plus or minus B sine theta. A and B are always considered positive values, so if it's like, 2 minus 3, so if we had this, like 2 minus 3 cosine theta, A would be 2, B would be considered 3. The minus just tells you what's going on with the overall equation. Now, when compare A versus B, you're going to create these 4 different types of limicons. So the inner loop is the one where A is less than B. So, for example, the one I just wrote there, 2 minus 3 cosine theta, would create an inner loop limicon. If A and B are the same, you're going to create what's called a cardioid. It kind of looks like a heart almost, with how it's shaped there, kind of going through and then kind of hitting it and bouncing back up again. Dimpled limicon is when A is bigger than B but still smaller than twice B, and it's starting to get a little flatter right here on the one side, whereas the convex limicon is very flat on the one side. This is where A is greater than or equal to 2 times B. All right, so each one of these graphs is still created the same kind of way. We're still using that table. We can recognize, though, that this will be a looped one because A is 1 and B is 2. So we should create an inner loop when we go through this. So, same setup. Go to the y equals, it will say r, 1 plus 2 sine theta. You might need to reset your table set, so go back to second window. Make sure your table set is starting at 0. The delta table should stay pi over 12, which I believe is 0.26, something from there. So that part shouldn't really change. So you'll find if we look at the first part of it from 0 to pi over 2, we got a 1, 1.5, 2, 2.4, 2.7, 2.9, and 3. So 0, 1 will start here. 1.5 is halfway between the 1 and 2 ring. Pi over 6 is on the 2 ring. 2.4 is right under half of it. 2.7 is a little bit past half. 2.9 is practically on the 3. And then 3 is on there. So we're kind of creating the same kind of shape we had from the circle so far. But you'll see it wasn't starting at the origin, so it's not going to be quite a full circle there, and that's where the whole inner loop part's going to come into play. So our next part, the pi over 2 to pi situation. So now it's going to repeat itself back down. So you're going to notice this is going to be 2.9, 2.7, 2.4, 2, 1.5, and then 1. So it's symmetric on the opposite side. This is where, again, symmetry can help us create this. We're not doing all these calculations with the calculator if you couldn't just do a table of values. So you got 2.9, 2.7, 2.4, 2, 1.5, back to 1. So we have that portion there. Now on the other side, the other half here, we're going to have 0.5, 0, negative 0.4, negative 0.7, negative 0.9, negative 1. So 0.5 is almost back to the pole. 0 then is in exactly at that pole position. Negative 0.4, so it'll be on the opposite side now. So at the 5 power 4, so it's equivalent at like power 4, so it's going to be over here. Negative 0.7, negative 0.9, and negative 1. We're going on the opposite side there because r is negative. And then you can kind of see where we're creating this loop on the inside, because now it repeats itself, negative 0.9, negative 0.7, negative 0.4, 0, 0.5, and then ending at 1. It should always end exactly where it started. So the negative 0.9 is going to go here because it's on the opposite side from where the angle is. The negative 0.7. Don't drive yourself too crazy trying to plot these things. It gets a little crazy when the decimals are so small. Back to 0, so it kind of creates, there's your inner loop. And then we have our 0.5 and then back to 1. So that's our overall shape right there. You can see it's creating that inner loop for that. And if we tried different Limicons that had different relationships between A and B, you would see you would have the kind of heart shape or when A and B are the same, and then becoming more flattened when A is larger than B. How flat it is depends on how much bigger A is versus B. All right, so that's our Limicon. Next up is our rose. So the rose is going to pretty much create these flower petals where the number of petals is going to correspond to the coefficient of theta. So the format here is R is A cosine n theta, or R equals A sine n theta. N has to be bigger than 2. It has to be an integer as well. Now, if n is odd, that's how many petals you'll have. So you'll see here, for this one, n is 3, there are 3 petals. N is 5, we got 5 petals. But when n is even, we have double that for the number of petals. So n is 2, we've got 4. N equals 4, we have 8 petals in total. And you'll recognize this is a rose versus a circle because it's got the coefficient of theta. So this is going to be a rose, and because n is 3, there should be 3 flower petals for this. And that's important because as we go through our pattern here, you might have a situation where once you create 3 petals, it's just going to repeat itself on the other side. So we start off here, again, our 0 to pi over 2 region. We'd have 6, 4.2, 0, negative 4.2, negative 6, negative 4.2, back to 0. So 0, 6 is going to be out over here. 4.2, a little bit past the 4 ring. 0. So once we get to 0, I'm going to kind of like show off how that looks. So there's that portion of that. Pi over 4 is negative 4.2, so we go on the opposite side. So 1, 2, 3, 4, so it's going to be over here. Negative 6 with pi over 3 is going to be here. Negative 4.2, pi over 12 is there, and then back to 0 for the pi over 2. So you can see here's where your petal is being formed. So we got half of one petal and a full petal in that region there. At 7 pi over 12, looking at this one, we now have positive 4.2. And you're going to notice it's just repeating between 4.2 and 6 back to 0. And then obviously on the negative side, once you go through your positive relationships. So then that's negative 6 right there. So we have 7 pi over 12 is going to be 4.2. So 1, 2, 3, 4. So right about there. 2 pi over 3, it's 6. 3 pi over 4, it's back to 4.2, and then back to 0. So there's that petal. And then at 11 pi over 12, which would be over here, it's now going to go across to negative 4.2, so it's equivalent to 23 pi over 12. And then pi is negative 6, so it's going to cross to 0. And we're going to create here, and you can see we now have everything we need. It's now create our 3 petals. We don't really need the rest of the table. It's just going to follow the rest of the pattern as you'll see. So at 13 pi over 12, you're going to get a negative 4.2. It's following the negative pattern there, and then to 0, and then positive 4.2, 6, 4.2, back to 0, and then negative 4.2, negative 6, negative 4.2, back to 0, positive 4.2, positive 6. But you were supposed to create 3 petals, and that's exactly what we did here. Now, that would have been the same 3 petals whether it was sine or cosine, just sine would be a little bit different in the shape of where the petals go. So it doesn't care about the trig function, it cares about the coefficients. So here, n is 2, so it's going to create 4 petals, 4 flower petals for this graph. So again, looking at our first region, 0 to pi over 2, you're finding you have 0, 2, 3.5, 4, 3.5, 2, and then 0. So it's just going to follow that particular pattern. So we started 0, 0. Pi over 12 is 2, and then 3.5, and then 4. Back to 3.5, back to 2, back to 0. So you're going to see each region, each quadrant is going to create one of the petals in this case, because there's 4 of them. And we're just going to follow that pattern. So you're going to see 7 pi over 12 is now negative 2, so that's negative 3.5, negative 4, back to negative 3.5, back to negative 2, back to 0. So it's negative, so it's going to be essentially over in the 4th quadrant, those locations. So 7 pi over 12, the negative 2, 7 pi over 12 is going to go over here. And then the negative 3.5, negative 4, negative 3.5, negative 2, back to 0. So here's the next petal. Then the 13 pi over 12 region. So you can see now we're going back to the positive stuff. So that's 2, 3.5, 4, 3.5, 2, back to 0. And again, if your calculator is showing you like E with a negative like 7 kind of thing, that's 0. Just so that, because sometimes the calculator gets a little weird with that stuff. That's going to be important with the last graph. We'll get into that. So pi is back at 0. And then 13 pi over 12 is 2. Ignore those weird horizontal vertical lines. I don't know why that just happened. I think it's with the iPad and my pen here. 3.54, 3.5, 2, back to 0. So here's our third rose petal. And then our final one, so we're going to find this is negative 2, negative 3.5, negative 4, negative 3.5, negative 2, and finally back to 0. So our final pattern's there. So again, it's negative 2, so it's going on the opposite side of the 19 pi over 12. So here, right there. Negative 3.5, opposite side, negative 4, negative 3.5, negative 2, back to 0. There's our fourth rose petal. All right, and that's why we want to be using the pi over 12s, even though they're not showing up on the unit circle, because it's helping create the overall shape. Without them, it's going to be, you can still create them, but your petal's going to be a little narrower. This kind of creates them a little wider, so it's better to see that. All right, so those are your roses. The biggest key is really recognizing how many petals there should be, and then once you've gotten the correct number, you just recognize it's going to repeat itself. So an odd number of petals, for the most part, will be done after 0 to pi. And then it repeats itself in the second half there, whereas even number, you'll need all of it to kind of create your overall shape. The final thing is the lemniscates. This is now based on r squared, and then it's a squared cosine 2 theta versus r squared equals a squared sine 2 theta. So to graph these things, because again, we can't graph an r squared, you're going to have to graph the r equals the square roots of a squared cosine 2 theta, and the r equals the square root of the a squared sine 2 theta. So because you're graphing square roots and cosine sine can get negative, you're going to see different error values that will show up. All right, so the first thing we're going to do is, because again, we can't have the r squared, we're going to just take the square root of both sides. So what you're going to type into your r equals portion of the graph is going to be r equals 25 cosine of 2 theta. Now, what you're going to have to recognize is that there'll be certain times when cosine is going to give you negative values. So therefore, you can't have a negative inside the radical, and it's going to give you error message on the calculator. Cosine error message occur in the second and third quadrants there, but since it's 2 theta, it's going to kind of affect how that actually plays out. So we're going to find that at 0, you're okay, you're getting 5, and then you're getting 4.7, and then 3, and then 0, and you're getting error messages. Now, there might be some mistakes in regarding where they put the 0 there, because you're doing, like, the calculator is doing its best approximation for these decimals. It might actually skip over 0 and say an error instead. So you need to recognize it's going to be the number, there'll be a couple numbers there in 0, and then there's going to be 5 error messages that go in a row for a repeat itself. So if you ever have a situation where it's 6 error messages, make sure the 0 goes in the appropriate location. It's always going to match up with the pi over 4s are going to be your zeros when it's based on cosine. When it's based on sine, the zeros will be based on the zeros, pi's, and pi over 2s. And it's going to always follow the pattern of works, fails, works, fails, works. So following the same pattern there, after 0 would be 3, 4.75, back to 4.7, back to 3, 0, and then it's going to fail 5 times in a row because there's a negative inside the radical. And then after the 0 goes back to then 3, 4.7, and then 5. So plotting this, so we're plotting 0, 5 to begin with, and then 4.7, so a little underneath it, and then 3 about underneath it, and then 0, so then it's done. So that portion right there, you can kind of see kind of like a flower petal almost. It's creating an infinity symbol, or like a bow tie. What's nice about these is r will never be negative, because just the square root portion there, so we're not going to worry about plotting negative portions of that. We're just going to be skipping over whole sections. So then 0 again is at 3 pi over 4, then it's 5 pi over 6, 3. So 1, 2, 3. There's our 5 pi over 6. 4.7 is going to be close to the 5, and then we're at the 5. And then back to the 4.7, back to the 3, and then back to 0. So we're going to create this portion of our infinity symbol. Again, I'm not quite sure what the vertical lines, what they're doing there. There's nothing wrong with my Apple Pencil. I'll work on that. Then 7 pi over 4 is at 0, and then 11 pi over 6 is at 3, and then 4.7 and then ending at 5. So there's our last bit for the infinity symbol. All right, so it's always going to create an infinity symbol. It'll either be flat horizontal infinity like we have here, or it'll be angled when we talk about the sine 2 theta. And again, it's always 5 in a row for the failure points. Pi over 4s are always the zeros, and there'll be pi over 2s and pi's for zeros for its sign. And it's still always 5 in a row. All right, so those are your polar function graphs. Again, refer to the video kind of showing you how you can use the graph calculator to create the polar function tables in the TI-84 calculator section for that. So next up for Unit 10 is going through the different formulas we can use with these polar functions and everything else we can do with that. So I'll see you guys next time for those.